Okay. Hello, everyone. Um, Today we will be talking about some relatively new stuff in the literature, which is basically the concept of statistical convergence and some of its variants. Uh, I want to talk about uh, firstly the concept of natural density of subsets of natural numbers, which is crucial for the formal definition of statistical convergence. Uh, okay. Natural density. Okay, let K be a subset of natural numbers and K n denote the set the set of k's from cap k not exceeding the number n. And by this, we will be denoting the number of elements in Kn. So we say that if the limit as n tends to infinity of cardinality of Kn over n exists, then this unique number is the density or natural density of the set K. So since, as I said before, since we will be using this concept to define the statistical convergence of a sequence, we will refer to an important notation that was given by Friedi. He says that if a sequence satisfies a property P for all K, if a sequence satisfies any property that one can come up with for all K, but except a set of natural numbers having zero density. Then then we say that xk holds the property P for almost all k, and abbreviate this by a almost all k. So now we can give the formal definition of statistical convergence. A sequence of real numbers, as I said before, or complex numbers, x is statistically convergent to number L, provided that for each epsilon positive, the density of this set zero. That is, the limit xk minus 1 greater or equal to epsilon over n equals 0 as n tends to infinity. This also can be written by this notation. I mean, xk minus 1 is less than epsilon for almost all k. And this is usually written by statistical limit xk equals L. So we here we are dealing with the terms of the sequence whose outside of the epsilon neighborhood of L. As you can see, this means that xk's, the terms that is in the complement of the epsilon neighborhood of L, if such terms having indexes such that whose density is 0, then we say that xk is statistically convergent to L. So by the natural way of the definition, we can easily say that every convergent sequence with ordinary sense must statistically convergent to the same limit. Okay. So I would like to give you an example which is non-trivial. As I said, every convergent sequence can be considered as a trivial example of statistical convergence. But this one is a basic example that explain non-trivial situations for statistical convergence well. Let xk be defined by if k is a square, then xk is 1, otherwise it is 0. So for each epsilon positive, it is clear that we have this inequality over n less than or equal to root n over n. So taking limit as n tends to infinity, we obtain the statistical limit of xk is 0 while x is non-convergent with usual sense. So this is a basic non-trivial example. But as I pointed out yesterday, when we have new type of convergence method, we would like to have some examples, at least one examples that is not convergent with this new method. So this one is an example which holds the definition, but the second example does not hold this property, this definition. Okay. The sequence x 1 0 1 0 1 0 is not statistically convergent, since for each real number L, there exists a suitable epsilon positive such that the set of k's from natural numbers with this inequality is held has non-zero density. So this example shows that not every sequence from the set of all sequence spaces is statistical convergence. So as I said, since usual the ordinary convergence implies statistical convergence preserving the limit uh, statistical convergence is a regular summability method. Because as I said, it is so easy to verify that limit xk, if limit xk equals L, then the statistical limit of xk is the same limit given in the beginning. So this means that statistical convergence is a regular summability method. So most of the time mathematicians wants to know that if summability method is applicable for a sequence without not having to know the limit itself. So because of this, as the usual case of convergence, we want to give an equivalent to the concept of Cauchy sequence for any new method. So this is where we arrive at the concept of statistical Cauchy sequence. Okay. A sequence xk is statistically a statistically Cauchy sequence provided that for each epsilon positive there exists a natural number cap and epsilon, which is dependent on epsilon, such that the limit of this ratio equals 0. In other words, xk minus xn less than or equal for almost all k. then we call the sequence an statistically cautious sequence. So I will be sharing the first big theorem about statistical convergence, which was given by Friede. The following statements are equivalent. First, X is a statistically convergent sequence, and second, X is a statistically Cauchy sequence, and lastly, X is a sequence for which there is a convergent sequence. X is a sequence for which there is a convergent sequence Y such that K equals Yk for almost all K. This is an important equivalence theorem about the concept of statistical convergence. If we want to make sure that whether or not a sequence is statistical convergence, we can try to understand if it is statistical Cauchy or it holds this third property. This gives us a pretty meaningful and fruitful corollary. Which says if statistical limit of x equals L, then x has a subsequence y such that limit y equals L. This is an important characterization for seeing as a sequence is statistical convergent or not. If it is a statistical convergent sequence, then it has to have at least one subsequence which is convergent to the same limit with ordinary sense. So Friede, in his famous paper, also shows that statistical convergence cannot be included by any matrix summability method. Statistical convergence cannot be included any matrix method. Because of this theorem, we can underline a couple of remarks. First, by the natural definition of statistical convergence, one can easily confirm that statistical convergence cannot sum periodic sequences such this sequence. So since but we know that there are some methods that can assign a limit to this sequence. For example, Cesaro summability can give this sequence a limit, but this sequence is not statistical convergent sequence. So this remark alone shows us that statistical convergence cannot be included by any sorry, it's my bad. Shows us that statistical convergence does not include most of the classical summability methods. Therefore, statistical convergence does not include many classical summability methods. But nevertheless, we can think of at least some summability methods that can be included by statistical convergence. For example, let me write down. There are some summability methods that can be included by statistical convergence. For this, I'm gonna define the concept of strongly Cesaro summability. Let X be a sequence and P be a positive real number. If limit of this ratio is 0, then we say that X is strongly P Cesaro summable to L. So in one of the most cited papers of Connor, he showed that this method, which is strongly P Cesaro summability, strong P Cesaro summability, implies the statistical convergence. I'm gonna share with you this theorem. If X is strongly P Cesaro summable to the number L, then it is statistically convergent to the same number. And the converse of this is true for bounded sequences. Okay. Proof. For each epsilon greater than 0, we have plus LP. So we can have such a separation here. As you can see, both finite summation runs from 1 to n, but divided by this condition. This part we use the indexes such that this inequality holds, and this part we use the indexes such that the the converse of this holds. So this can be done without any problem. Okay, it is clear that this sum is greater or equal than each of these two. It is greater than each of this. We are gonna use just this one. So k runs from 1 to n, and we have the ones that holds this inequality. And we can easily write that it's greater than epsilon to the power p, and this number is actually exactly the cardinality of this set times epsilon to the power p. So dividing this dividing both sides by n and taking taking limit as n tends to infinity, we get statistical limit of xk equals L. So this completes the proof. So now we are gonna prove that the converse of this property is true for bounded sequences as well. So now let x be a bounded sequence and statistical limit of xk is equal L. Set the number k as the supremum norm of x plus absolute value of cap L. So this is a fixed number. It is just the norm of this sequence, which is bounded, and plus the absolute value of cap L. For each epsilon positive, we can select a fixed number of natural numbers cap n such that such that 1 over n times cardinality of this set is less than epsilon over 2 times cap k to the power p. We can write this inequality because x is statistically convergent to the number L. So now we can consider a set, consider the set cap Ln such that it has some numbers not exceeding n, which holds this inequality. So okay, okay. This number, yeah, yeah, it's a fixed number. Sorry? No, no, yes, number as a verb. Yeah. Sorry, sorry, no problem. Yeah. Okay. Oh. Okay. Now, for all n greater than cap n epsilon, we have this equality. Xk minus L to the power p plus k not in Ln xk minus L to the power p. So we have two main two sub summation, sub finite summation here. One runs in Ln, but the other does not run in Ln. But we don't want k exceed n. So we can write that because of the definition of cap k, we can write that the first summation with 1 over n is less than or equal to n times epsilon over 2 times k to the power p times k to the power. And this part is much more easy. 1 over n times epsilon over 2. So this gives us epsilon over 2 plus epsilon over 2, which is epsilon. So for all n's greater than cap n epsilon, we have this inequality. This shows that holds which yields that X is strongly P zero summable to L. Yes, we can take a break now if you want, and if you want to make any point or discuss any issue, I would like to hear it. Okay, thank you. You can take a break if you want. Okay. So I'm gonna pause both